All right, so quick overview of a hypothesis test related to some of the last few problems. So either to use the right spreadsheet or to grab the right formulas or to grab the right stat key tool to do this, I have to decide once I have a hypothesis test, am I testing a mean or am I testing a proportion? So looking back at one of those problems, 28 we'll start with. What are we given here? We're told, oh yeah, we've seen this problem a few times in the assignments, that on January 31st, 2006, 9 of 30 stocks making up the Dow Industrial Average increased in price. And then it says, on the basis of this, a financial analyst claims we can assume that 30% of the stocks traded went up the same day. So they're saying, hey, this proportion is 30, they said, right, 9 out of 30, 30%. They're saying the proportion is 30%. So this is a proportion. So I gotta, if it's not clearly stating that, I gotta kind of figure out, did they add up a bunch of numbers and divide by how many, or did they just divide two numbers to get a percentage? And here they divided two numbers to get a percentage. So this is a proportion. So looking at this problem, I say, okay, I'm using a proportion. If I'm using a proportion, then I have to figure out what the null hypothesis is and the alternative hypothesis. And the null will have some kind of equal, right? So it's either going to be p equals something, or p is less than or equal to something, or p is greater than or equal to something. Alternative hypothesis can't have an equal. So the alternative to equal is usually not equal. The alternative to less than or equal to is often greater than, the opposite. And the alternative to greater than or equal to would be less than. Sometimes we set equal to as the null to go with a greater than or a less than, and that's okay too. So once I have those, the other thing to note is the standard error for a proportion in a hypothesis test, and that's always the square root of p times q over n, and that's all inside the root. And remember, q is always 1 minus p. The standard error tells me how spread out the sampling distribution is, and StatKey can help me figure that out too if I'm a little stuck on that to draw my picture. Otherwise, to get the p-value, which is usually the next most important thing, I need the data. So in this case, the data is usually going to be related to p prime, which is x over n. And you have to be given two of these three things. If you're given x over n, you calculate p prime. If you're given p prime and n, you can calculate x. So you'll be given two of these three, sometimes all three of them. And then for the p-value, that's you gotta figure out whether it's a left tail, right tail, or two tail, and the spreadsheet pretty much does that for you. And the spreadsheet uses the norm inverse formula in some way. So it has something to do with the norm dot inverse. And it may be 1 minus the norm dot inverse, it may be twice the norm dot inverse. It just depends on whether it's a two tail, right tail, or left tail. And the spreadsheet just deals with that for you. And we'll look at this problem in a minute. And then the norm inverse always wants to know what is your sample information. So it would want p prime first, then it wants the population mean, so I would give it p next, and then it wants me to give the standard error next, which is that square root up there. And I think that's all it asks for. We'll consult the spreadsheet to double check. And there are so many spreadsheet formulas. I know a lot of them off the top of my head, but I usually have to look them up. So p-value for a proportion, I got to go to the right tab. And it does, oops, oh, I lied, shit, it's the norm dist, not the norm inverse, eek. And it should be norm dot dist, but that's okay. Close enough. All right, so I just lied. It's the norm dot, oops, norm dot dist, or norm dist, which does the same thing. And there may be a 1 minus on that, and you may have to double it if it's a two-tail. But it still wants, okay, I remember the other thing it wants. It wants to know if it's true or not, and it's always true next. So I would enter P prime, P standard error, which could be that whole square root unless you pre-calculated it, and then it wants a true or a 1 next. And again, that's in the spreadsheet. All right, so that's kind of the setup there. The other problems that you asked about here, 29 and 30, give us a mean. So here they're talking about the average length of a lag bolt, and it talks about means and averages in here. And the next one talks about the mean score on a first statistics test. And so there's some debate over what is it? Is it 65? Is it bigger? Is it less? So back to the drawing. So for a mean, you have to decide if you're going to use a normal distribution or you're going to use a t distribution. So let's draw, let's see, switch colors maybe. So either for the mean, you're going to use the normal distribution, which is often called a z-test, or you're going to use the t distribution, which means you're applying what's called a t-test. And how do you decide? Typically, you kind of lean toward the t-test. So it's the t-test if it's a small sample, or it's you don't have this population standard deviation. No known population STD. And that's the value that we call sigma. So a small sample, and I don't know the population standard deviation, I should use sigma. Even if you don't know sigma and it's a large sample, you should still use a t-test. It's a normal distribution if you definitely know the population standard deviation. So we do know sigma. And again, that's the thing we call sigma. So if we do know it, then that's the way we go there. And then otherwise, it's pretty similar. I have to set up a null and alternative hypothesis. And the standard error formula is different. So the standard error formula, if you're doing a z-test, and again, the spreadsheet has this built into it, would be sigma over the square root of n. And then the standard error for a t-test would be S over the square root of n. So since we don't know the population, oops, wrong letter. Since we don't know the population standard deviation, we let S be a substitute for it. And a t distribution just tends to be a little bit wider than a normal, but it's still a symmetric bell shape. And it's kind of to make up for the fact that we don't know, we have less information. And think about it, if the mean is questionable and we're testing it, how on earth would we know the standard deviation of the population accurately? So typically, this is the more common path here in reality. That people go down when they're testing means. And then the p-value is calculated in the spreadsheets, but you would have to use a normal dist to calculate the p-value here. So p-value is some version of a normal dist. Kind of like that over there. You would want x bar, you would want to enter mu, and you would want to enter, let's see, mu sigma over the square root of n. That's the standard error. Let's just label it as standard error, and then true. If we're down the t-test path, and it's a bit more complicated, we would have to find the test statistic here first, and the spreadsheet does that. And the test statistic is t equals the sample data minus the null hypothesis divided by S over the square root of n, that's standard error. Once I get that t-score, then I can calculate the p-value. by using some form of a Ttest. So T.dist. And the spreadsheet doesn't care whether the formulas are uppercase or lowercase. Sorry, I'm switching case. And it's going to want to know what's your t-score. And what else does it want? It wants n-1. And I think it might want true after that. Let's double check the spreadsheet. And then there's different versions of the t-test. There's a right tail, there's a two tail. That make life easier. And the spreadsheet should have those built in. So hypothesis tests, come here, please. There we are. And t-test. And then either there's two versions of the spreadsheet here. There's the left side that says you don't have the sample data, you're just given the summary statistics. Or the right side says you know the sample data, you have it, so you would just replace whatever's in this column with your sample data. And then here's the test statistic calculation, which if you don't have this, like if, let's see, I didn't add the test statistic till like Wednesday of last week, so you might not have the updated version of this. So if that's the case, let me know, and I'll get you the version that in row 19 says, here's the test statistic. And again, that just says, take the sample mean, subtract the null hypothesis mean, and then divide by the standard error. And that gives you the t-score. And then based on the t-score, yeah, it wants to know that 1 or a true at the end. So the right tail uses the Ttest formula. Let's see. Next one also used the Ttest. And okay, I had them all use just the Ttest formula. Okay. So that is the overview. And often if you're not sure how to draw the picture to go with, like the spreadsheet here, stat key is not a bad place to go to draw pictures to go with that. And if it's a z-test, you're drawing a normal. If it's a t-test, you're drawing a t, and you just need to give it the correct information to draw that. So let's pick one of these and do it. I've recorded the stock market one several times. So at the end of the playlist, there's 2 or 3 recordings of problem, what's problem 28 here, because it came up in the last week's assignments. So I'm not going to do that here. If you want to see a video of it, there's several available. We could either do the Bolt one, or we could do the one about the class scores. So let's see, Gideon asked about this. Gideon, what would you like to do? Problem 29 or 30? See, is Gideon still here? Yes, okay, problem number 29. So that was the Bolt one. Okay, so let's copy that information into a new page, and then double check we have all the relevant information. Okay, so yeah, everything is in the top there. So back here, so before I hit a spreadsheet, I'm just gonna kind of figure out what the hell is going on. So the population is lag bolts. So we have lag bolts, and we can measure things about lag bolts, like how heavy are they and how long are they, and what's the design of the thread. And we're looking for their length. So just gonna make a note here that my parameter, because I'm gonna need to know that if I have to make a conclusion in writing, is the average length of what we call a 10-inch lag bolt. Okay, so the machine was recently redesigned, and there's wondering, is it still producing 10-inch lag bolts, or are they significantly smaller or significantly larger? So it just here in that second sentence, they're just wondering, is it still producing 10-inch lag bolts? So question, does the average length still equal 10? So that's the only question I have so far. You've gathered a random sample of bolts that have been produced with this new process. Conduct the appropriate hypothesis test at a 5% significance level to determine if the overall mean of this process is 10 inches. So since I have nothing else to go on but, hey, is it 10? That equals means this has to be the null hypothesis. And my only suggestion for an alternative is to say, well, I guess the alternative is not 10. So right away, this is a two-tailed test, which means I got to remember to double that p-value. I need both tails, so two-tail test. If I want to sketch out what might happen here, I know the center, according to the null hypothesis, is 10 inches. Next, I need to, based on the data here, calculate the standard error. Because notice they don't tell me the population standard deviation. Nowhere here does it say the population standard deviation is. And if I go back to the original question, and I just do a quick search here, Control F, population, comes up here at the top, and that's the only place that's highlighted. So they don't give me the standard deviation of the population, which means I have to use a t-test. Now they told me that here, but I'm just reminding you, like I won't always tell you which test to use. You have to decide that sometimes. Here I say, hey, use a t-test, please. Okay, so I have to use a t-test for one of two reasons. I don't know the population standard deviation, and this is a small sample. So I need to get this data into my spreadsheet. And although I could do a simulation on stat key, it doesn't specifically address stat key. So stat key might give me more, a slightly different p-value than the computer's expecting, although it should be in the ballpark. All right, so what are we doing? We have a mean, we have a t-test. So back on that hypothesis test spreadsheet, I need to get into the t-test place. And I was given the sample data, so I want to scroll over here to the right side of the sheet. And on mine, I drew a big dark bar there to remind myself these are two different parts of the sheet. And then I need to get that data in here. So to do that, I'm just going to delete a bunch of stuff. Zoom out to do that for a sec. So make sure there's nothing else in the region, delete. And then I'm going to paste it off to the side first because it's in rows. I want columns. So what I can do there is then re-highlight, re-highlight all of this, cut it, Control X, and then there's a insert option or paste option called paste transpose, which will flip the rows to columns. So I just start in the right spot. Otherwise, I have to retype them, which is a pain in the butt, or do a lot of copy and paste. So I'm going to paste, transposed. So that's just less typing for me. And then I got to move these guys, Control X, down here, Control V. All right, so I have my data in the right column. And according to this, there should be 16 numbers. So looking back at the problem, 2, 4, 6, 8, 10, 12, 14, 16, starting with the 9.92, ending with 9.93. Just want to make sure I copied the right stuff. Yeah, looks like I got that right. Okay. This extra stuff on the right is no big deal. You could leave it or delete it. All right, so I got my data in there. It's calculating the mean of that. And it's also looking at some blank cells. And since the cells below are empty, it's no big deal. It says the mean is 9.9856. For my data, yours will be a little different. Let me blow this up again. It's telling me how many are in the sample and it's telling me the standard deviation for the sample. Then over here, it calculates the standard error, which says, hey, take your sample standard deviation, divide by the square root of your sample size. We need that number to draw an accurate picture. The t-statistic, mine says 878. That's insane. A t-score is usually going to be like between -3 and 3. Sometimes you might get something like at 7, 8, or 9, but not 800. So what that means is I forgot to enter the correct null hypothesis. So my null hypothesis was that the mean was 10, or it was not 10 for the alternative. I still have a not equal to like my previous example, so I'm not going to change that. I'm still doing two tails, but now I should get a more reasonable test statistic. So a t-score is like a z-score. It counts standard deviations. In this case, it's counting standard errors. And so what it says is 9.9856 is less than 10. It is 1.2, 1.3 standard deviations below average when we're expecting the average to be 10. So the question, is that way below average, or is it close enough to 10 for 16 volts? And the p-value tells us that. So I want the two-tail version. Two-tail version, I'm getting a p-value of 22.5% down here. Other number was a residue from the previous problem. And that's a pretty big p-value. So that means I can't reject the null. So the null said that the average bolt length was about 10. And what we're finding is to find an average of 16 of them, that's 9.9856 inches, is close enough to 10 to say the machine works properly, is what we've decided here. Okay, so I'm going to estimate the standard error to be about 0.1. And then, I mean, if you round this like to 3 decimal places, what would you get? 9.986. If you round it to 2 decimal places, you get 9.99, right? So this number is pretty close to 10. So how to draw the picture next, and then we'll do our conclusion. So in order to figure out where my sample mean falls, I got to know what the standard error is, because the standard error says how wide is one of these standard deviations here. So typically I need to work with about 3 standard deviations on either side. We know our mean is to the left. It was 9.985.6, I think, if I had 4 decimal places. Come on. 9.9856. Yeah, let's throw 4 decimal places. My standard error to 4 decimal places was, I'm going to go 3 decimal places because it's easier to count, 0.1011. Back to my drawing. All right, so let's round this to 3 then also. So that would be a 6 there. The other thing so I need to know where that falls. To figure out how far away from the mean it falls, I need the standard error. And we're approximating, based on the spreadsheet, a standard error of 0.011, at least my version of the data. Yours will be a little different. And I usually just round that to be a nice enough number for me to draw. So this number over here, I'd have to subtract the 0.11. So what would that be? 9.989 would be that, and then subtracting that again gives me 9.978 would be the second standard deviation. I have 9.986, which is slightly closer to the first standard deviation to the left. So as far as t-scores go, this number right there has a t of -1 because it's 1 standard error below the mean. This number here has a t-score of -2 because it's 2 standard errors below the mean. My number here for x bar is a little bit closer to the -1 than -2. It sits about right there. And remember, the spreadsheet calculated for me that number right there is my x bar, 9.986, and the computer said its t-score was about -1.26-ish, if I remember right. Yeah, -1.26 there. So that's not unusual, really, right? Because the p-value, that percent on that side, desktop again, that was about 11.3% on just the left side where I'm at. And again, it can't calculate the right side at the same time because it has troubles with negatives, the Ttest does. So if the t-score is negative, then you get a left tail, not a right. If the t-score is positive, you get a right tail, not a left. And the two-tail just doubles whichever one exists. So back to my picture. That was about 11.3-ish. So over here, I get about 11.3%. Because this is a two-tailed test, I got to remember to reflect that over here. And I don't care what that number is right there. All I know is that this is 11.3% also. And because I have a two-tailed test, my p-value is both tails. So this p-value is about 22.6% roughly to 3 decimal places. That's just a decimal. So don't forget that. All right, so we're getting there. So let's see, that's a big p-value, right? It's definitely bigger than 5%, so that means we fail to reject the null, fail to reject null hypothesis. And when I'm forming my conclusion, I'm kind of thinking about my audience too. So my audience is the guy who owns this plant or the guy who runs these machines, and he wants to know, hey, is the machine working right? Are they pretty close to 10 inches on average or not? And since I failed to reject the null, my data supports the null because I'm failing to reject it for the alternative. The alternative was, no, they're not 10 inches. Yeah, these are close enough to 10 inches. So this was my decision. My conclusion then is based on what this group would like to know. So new page, conclusion. Let's see. I could use the phrase sufficient evidence, or I could just say the sample data supports. I think I'll do it a couple ways. So I could say the sample data, which was the average of 16 lag volts, supports the claim, oops, that the average length is 10. Is 10 inches. I'll do another version in a second. Let's see, there's a message in the chat. Yeah, so the data is different each time. When you put that mu is equal to 10, it said that it was wrong. So, okay, so each time you generate this problem, it's gonna be a little bit different, and yours won't be exactly the same as mine. So on mine, let's see, choose the correct alternative hypothesis. So my alternative hypothesis was that mu is not 10. Right, the null hypothesis was that it is 10, and here it's saying, hey, what's the alternative? So that would be mu is not 10. Do I have the necessary conditions? Well, if I don't, I can't do the problem, so I'm just gonna say, yeah, I do. So I'm gonna believe those conditions are true, otherwise there's no point in continuing. And then I would enter my sample mean from the spreadsheet, so, and this one doesn't tell me how much to do. So since the data has 2 decimal places, I would want to enter 3 decimal places. So then I'm going to call it, for mine, 9.986. And again, yours, you'll have a different set of numbers here. You won't have the same ones as me. Your standard error, for me, mine was 0.0113, I think. If I throw an extra one in there for fun, sometimes that's dangerous. 4. The test statistic it calculated for me, mine was negative 1.26 something something. I'll give that at least 3 decimal places. T. So 265. Let's go with that. Should be good enough. My p-value was about 0.226, but I may not have done a good job rounding that. 5.1. Okay, we'll go 5.2. And then decision, fail to reject or reject. That's a big p-value, so I'm going to fail to reject. Then it's a matter of which is the correct conclusion, and that's why I usually write my own first. So the evidence seems to indicate that the mean production length of these lag bulbs differs from 10. No, we found it pretty close to 10 because the p-value is so big. We cannot conclude that the mean production length of these lag bulbs differs from 10. Yeah, we can't conclude it's different. It's too close to 10. So for me, it's this one. And again, you may have a reject. Okay, so your problem had a different set of 16 lag bolts, or you might even have different than 16. So I'm just going to submit mine for fun, and I got them right. And if I try a similar one, which you should do if you got help on a problem, I have a different set of numbers here. I'm not gonna end up with the same results I had before. So my mean, my standard error, my t, my p-value will all be a little bit different, and I may have a different decision and conclusion to make on that one. And that is like the harder part in drawing the picture. Again, to draw an accurate picture, you need to know the standard error. So it doesn't matter whether you're talking about a proportion, a z-test, or a t-test. The standard error tells you, based on the center being the null hypothesis, about where your sample data falls. Does it fall close on the left or far on the left? Does it fall close on the right or far on the right? And the only way we can measure that is if we calculate that standard error. And the central limit theorem gives us a theoretical way to do that. Otherwise, we'd have to enter all this data into StatKey and see what StatKey thinks about it when it bootstraps it. So we could use StatKey bootstrap. Since this problem didn't say bootstrap the data, then I could end up with a p-value that's a little bit off, like maybe 20% or 25% instead of the 22, 23% I have here. Okay, so let's see. It is nearing the end of the hour, so I'm going to stop here. I'll be back online at 10 o'clock tomorrow. A couple people emailed me this weekend, so I spent a lot of time writing to students, and I did a couple of special sessions this weekend. If you need extra help on anything, message me from a problem. And if you think you need a special Zoom session, I'll be glad to record that with you too.